Welcome to Lesson 1.2, Networking Basics. In this lesson, we're going to explore how systems communicate over networks. This is one of the most important topics in cybersecurity because every cyber attack happens through network communication. You'll learn key concepts like IP addresses, DNS, and ports, and how data flows between devices. More importantly, you'll begin to understand where attacks can happen within that communication process. By the end of this lesson, you won't just understand networking. You'll start thinking like a SOC analyst, identifying what is normal and what could be a threat. Let's get started. Let's take a deeper look at some of the key ideas behind networking basics and why they are so important in cybersecurity. First, we have communication protocols. Protocols are essentially the rules that govern how data is transmitted between devices on a network. They define how information is formatted, sent, received, and interpreted. Without protocols, devices wouldn't be able to understand each other. For example, when your computer communicates with a website, both sides must follow the same set of rules to ensure the data is exchanged correctly and reliably. Common examples of protocols include HTTP for web traffic, HTTPS for secure communication, and TCP/IP for general data transmission. So protocols ensure that communication between systems is structured, reliable, and efficient. Next, let's talk about unique network addresses. Every device connected to a network has a unique identifier known as an IP address. This address allows data to be sent to the correct destination. Think of it like sending a letter. Without the correct address, the message would never reach the intended recipient. When you access a website, your request is sent to a specific IP address, and the response is sent back to your device's IP address. This precise addressing system is what allows billions of devices to communicate across the internet without confusion. Finally, let's connect this to cybersecurity. Understanding networking is the foundation of cybersecurity. Why? Because all cyber attacks happen through networks. If you understand how data flows, how devices communicate, and how systems are addressed, you can begin to identify when something is not normal. For example, unexpected communication between devices, data being sent to unknown IP addresses, unusual traffic patterns. These are often early signs of a potential security threat. So in summary, protocols define how communication happens, IP addresses define where communication goes, and networking knowledge allows you to secure that communication. This is why networking is one of the most important skills you need to develop as a future SOC analyst. Let's now explore why networking is so important, especially in the context of cybersecurity. First, networking forms the foundation of IT communication. In today's digital world, almost every system is connected, whether it's computers, servers, mobile devices, or cloud services. Networks enable these systems to communicate, share data, and perform tasks efficiently. For example, when you send an email, it travels across multiple networks. When you access a website, your request is sent to a remote server. When organizations run applications, they rely on network connectivity. So networks are essentially the backbone of modern technology. Without them, most digital services would not function. However, this connectivity also introduces cyber attack risks. Because systems are connected through networks, attackers often target these connections to gain access. Instead of attacking a system directly, they may intercept data, exploit weak network configurations, or use network pathways to spread malware. For example, an attacker might intercept unencrypted data. Malware may spread from one device to another across a network. Unauthorized access can occur through poorly secured network points. This makes networks one of the most critical areas to protect in cybersecurity. This is why understanding networking is essential for defense. When you understand how networks operate, you can begin to identify where weaknesses may exist. You can detect unusual traffic patterns, suspicious connections, communication with unknown or malicious systems, and more importantly, you can take action to defend against these threats. A strong understanding of networking allows you to identify vulnerabilities, monitor system behavior, protect communication channels. So in summary, networks enable communication and power modern systems, but they also create opportunities for cyber attacks. and by understanding networking, you gain the ability to defend systems more effectively, which is a key skill for any SOC analyst. Now let's go over some essential network definitions that form the backbone of how communication happens across systems. First, we have the IP address. An IP address is a unique identifier assigned to every device on a network. It allows devices to locate and communicate with each other accurately. Think of it like a home address. If someone wants to send you a letter, they need your exact address to ensure it reaches you. In the same way, when data is sent across a network, it needs a specific destination, and that destination is defined by the IP address. Without IP addresses, data wouldn't know where to go, and communication between devices would not be possible. Next, we have DNS, or the domain name system. DNS acts as a translator between human-friendly names and machine-readable IP addresses. For example, when you type a website like google.com into your browser, your system doesn't actually understand that name directly. Instead, it sends a request to a DNS server, which translates that domain name into an IP address. This makes the internet much easier to use because we don't have to remember complex numerical addresses. Finally, let's talk about ports. Ports are like entry points or doors on a device that allow different types of communication to happen simultaneously. For example, web traffic uses specific ports. Email uses different ports. Other services use their own designated ports. This allows a single device to handle multiple types of communication at the same time without confusion. So ports help organize and manage network traffic efficiently. Key takeaway: IP addresses tell us where to send data, DNS helps us find the destination, and ports determine how the data is handled once it arrives. Understanding these three concepts is critical because they form the foundation of how systems communicate and where cyber attacks can occur. As a SOC analyst, you'll often analyze traffic based on IP addresses, DNS queries, and port activity to detect suspicious behavior. Now let's break down some essential network definitions that form the foundation of how systems communicate. We'll focus on three key concepts: IP addresses, DNS, and ports. First, the role of IP addresses. Every device connected to a network, whether it's your laptop, phone, or a server, has a unique identifier called an IP address. This address allows devices to locate and communicate with each other across the internet. Think of it like a home address. If someone wants to send you a letter, they need your exact address to make sure it reaches you. In the same way, when your computer sends a request, for example, to open a website, it needs to know the exact IP address of the destination server. Without IP addresses, communication between devices simply wouldn't be possible. Next, let's look at DNS, the domain name system. DNS acts as a translator between humans and computers. As humans, we prefer to use easy-to-remember names like google.com, but computers communicate using IP addresses. So when you type a website name into your browser, DNS converts that name into the corresponding IP address. That's why DNS is often described as the phone book of the internet. It allows you to access websites easily without needing to remember complex numerical addresses. Finally, we have the purpose of ports. Ports are entry points on a device that direct incoming data to the correct service or application. Think of a device like a building and ports like different doors. Each door leads to a different department or function. For example, web traffic typically uses port 80 or 443 email services use different ports. Other applications use their own designated ports. When data arrives at a device, the port number tells the system where that data should go. This ensures that the right application receives the right information. So to summarize, IP addresses identify where data should go. DNS helps us find those addresses easily. Ports determine how and where data enters a system. Together, these components make network communication possible. And as a future SOC analyst, understanding these basics will help you recognize how systems communicate and, more importantly, how attackers might try to exploit that communication. Let's now walk through how system communication actually happens when a user accesses a website. This process may seem simple from the user's perspective, but behind the scenes, several important steps take place. We start with the initial request to DNS. When a user types a website name, for example google.com, into their browser, the device does not yet know where that website is located. So the first thing it does is send a query to the domain name system, or DNS. This is essentially the device asking, what is the IP address of this website? This step is critical because computers communicate using IP addresses, not names. Next is IP address resolution. The DNS server responds to the request by providing the correct IP address associated with that domain name. This allows the user's device to know exactly where to send the request. Think of this as getting the exact location of a destination before sending a message. Without this step, the device wouldn't know where to direct its communication. Finally, we have the request and response cycle. Once the device has the IP address, it sends a request directly to the server hosting the website. The server receives this request, processes it, for example, by retrieving the web page data, and then sends a response back to the user's device. This response contains the content needed to display the website. All of this happens in a fraction of a second, allowing the page to load almost instantly. Now here's why this is important for cybersecurity. Every step in this communication process can be monitored and potentially exploited. For example, DNS requests can be redirected to malicious servers. Communication with unknown IP addresses may indicate suspicious activity. Unusual patterns in requests and responses can signal an attack. As a SOC Analyst, your role is to understand this flow and identify when something doesn't look right. So to summarize, the user requests a website, DNS, translates the name into an IP address, the device sends a request to the server, and the server responds with the data. This entire process forms the foundation of how systems communicate and how many cyber attacks take place. Let's break down the website access flow step by step, so you can clearly understand how systems communicate when a user visits a website. We begin with the user entering a website URL. When a user types a web address, for example google.com, into their browser, they are initiating a request to access a specific resource on the internet. At this stage, the browser knows the name of the website, but it does not yet know where that website is located. So the process of communication begins. Next is DNS, resolving the domain name. The browser sends a query to the domain name system, or DNS, asking for the IP address associated with the website name. DNS then translates that human-readable domain name into a machine-readable IP address. This step is essential because computers communicate using IP addresses, not names. After that, the browser sends a request to the server. Now that the browser knows the correct IP address, it sends a request to the web server hosting the website. This request is essentially asking, please send me the content for this web page. This communication is done using protocols such as HTTP or HTTPS. Finally, the server processes the request and responds. The server receives the request, processes it, for example by retrieving files, running scripts, or accessing databases, and then sends a response back to the user's browser. This response contains the web page content, which the browser then displays to the user. All of this happens in a matter of milliseconds. Now, from a cybersecurity perspective, this process is very important. Each step in this flow can be monitored, analyzed, and potentially targeted by attackers. For example, DNS can be manipulated to redirect users to fake websites. Requests can be intercepted. Servers can be compromised. This is why understanding this flow is critical for a SOC analyst. So to summarize, the user enters a URL. DNS resolves it to an IP address. The browser sends a request, and the server responds with the content. This simple process is the foundation of how the internet works, and also where many cyber attacks take place. Now that we understand how systems communicate, it's important to look at the security risks involved in that process. First, let's talk about opportunities for cyber attacks. Every step in system communication, From the moment a user enters a URL to DNS resolution to server response can introduce potential vulnerabilities. If these steps are not properly secured, attackers can exploit them to gain unauthorized access, steal data, or disrupt services. This is why cybersecurity requires constant vigilance. Even a small weakness at any stage can become an entry point for an attack. Next, we have risk in communication channels. Whenever data is transmitted between systems, whether it's between a user and a website or between internal systems, there is a possibility that this communication can be monitored or intercepted. For example, data sent over unsecured connections can be captured. Sensitive information could be exposed. Attackers may observe communication patterns to identify targets. This makes secure communication protocols such as HTTPS and encryption extremely important. Finally, let's look at the importance of detecting abnormal behavior. In cybersecurity, one of the most effective ways to identify threats is by spotting unusual activity. This could include unexpected connections to unknown IP addresses, unusual spikes in network traffic, repeated failed login attempts. These are often early warning signs of malicious activity. SOC analysts rely heavily on recognizing these anomalies to detect and respond to threats before they cause serious damage. So to summarize, every step in communication presents potential risks. Communication channels must be secured to prevent interception, and detecting abnormal behavior is critical for identifying threats early. As a SOC analyst, your role is to monitor these processes closely and act quickly when something doesn't look right. Let's now look at a simple but very powerful tool used in networking and cybersecurity, the ping command. First, testing connectivity. The primary purpose of the ping command is to check whether your device can communicate with another system on the network, such as a website or server. When you run a ping command, for example, ping google.com, your device sends small packets of data to the target server and waits for a response. If the server responds, it means the connection is working. If there's no response, it could indicate a connectivity issue. This makes ping one of the simplest ways to verify network communication. Next, measuring response time. Ping doesn't just tell you if a system is reachable, it also measures how long it takes for data to travel to the server and back. This is known as latency. The output typically shows the time in milliseconds for each packet sent and received. Lower response times indicate faster and more efficient communication. Higher response times may suggest network delays or congestion. Finally, diagnosing connection issues. Ping is also very useful for troubleshooting network problems. For example, if packets are not returned, it may indicate the server is down or unreachable. If there is packet loss, it means some data is not successfully reaching its destination. If response times vary significantly, it may indicate instability in the network. These insights help identify where a problem might exist, whether it's your device, the network, or the server. From a cybersecurity perspective, this is important because SOC analysts use similar techniques and tools to monitor communication between systems. They look for unusual delays, failed connections, unexpected communication patterns. These could be early signs of network issues or even malicious activity. So to summarize, ping helps you test connectivity, measure response time, and diagnose network issues. It's a simple tool, but it provides valuable insight into how systems communicate, which is essential for both networking and cybersecurity. Now that we've run a network test using a tool like ping, the next step is to interpret the results correctly. This is a key skill for both networking and cybersecurity. Let's start with identifying the destination IP address. When you run a command like ping google.com, your system first resolves the domain name into an IP address. This IP address is displayed in the output. This tells you exactly where your data is being sent. As an analyst, this is important because you need to verify that the destination is correct and expected. For example, if you ping a trusted website, you expect a known IP range. If the IP looks unfamiliar or unexpected, it could indicate redirection or a potential security issue. So always check. Is this the correct destination? Next, we look at analyzing packet flow. Ping works by sending a number of packets to the destination and waiting for replies. In the results, you'll typically see packets sent, packets received. Ideally, these numbers should match. If all packets are received, it means the connection is stable. However, if some packets are missing, this is called packet loss. Packet loss can indicate network issues such as congestion, poor connectivity, or interference. In some cases, unusual packet loss may also point to filtering or suspicious activity. Finally, we evaluate response time. Each packet response includes a time measurement, usually in milliseconds. This tells you how long it takes for data to travel to the destination and back, also known as latency. As an analyst, you should look for patterns. Consistent, low response times leads to healthy network. High response times leads to possible delays or congestion. Sudden spikes or fluctuations leads to instability or abnormal behavior. These patterns can help you identify both performance issues and potential security concerns. From a SOC Analyst perspective, this is where real analysis begins. You're not just checking if something works, you're asking, is the destination correct? Is the communication reliable? Is the performance normal? Any unusual behavior could be an early sign of a problem or even a cyber threat. Now let's focus on a very important concept in cybersecurity, understanding the difference between normal and suspicious activity. This is one of the core skills every SOC analyst must develop. Let's start with characteristics of normal activity. Normal network behavior is predictable and consistent. For example, communication happens with known and trusted IP addresses. Response times are stable and consistent. Data flows follow expected patterns. In simple terms, everything behaves the way you expect it to. When systems are operating normally, there are no surprises. Connections are reliable, and traffic patterns are familiar. Now let's look at indicators of suspicious activity. Suspicious activity is anything that deviates from normal behavior. This could include communication with unknown or unfamiliar IP, addresses irregular traffic patterns such as sudden spikes or unusual timing, no response or failed connections, which may indicate blocked or hidden activity. These are warning signs that something may not be right. For example, a system suddenly connecting to an unknown country, repeated failed login attempts, unexpected outbound traffic. These could indicate a potential attack or compromise. Finally, let's talk about the importance of identifying these differences. The ability to distinguish between normal and suspicious activity is critical in cybersecurity. Why? Because threats are often hidden within everyday network activity. If you don't understand what normal looks like, you won't be able to detect when something is wrong. Early detection allows for quick response, which helps minimize damage and prevent escalation. From a SOC analyst perspective, this is your daily responsibility. You continuously monitor systems and ask, is this normal behavior? Does this match expected patterns? Or is this something unusual that needs investigation? This mindset is what allows analysts to detect threats early and protect systems effectively. So to summarize, normal activity is predictable and trusted. Suspicious activity deviates from expected patterns, and identifying the difference is essential for maintaining security. This is one of the most important skills you will develop in your cybersecurity journey. Let's now walk through how to test network connectivity using the ping command on a Windows computer. This is a simple but very important step, especially for troubleshooting and for understanding how systems communicate. Step 1. Open command prompt. First, we need to open the command prompt. You can do this by pressing the Windows key and the letter R on your keyboard. This opens the Run dialog box. Then type CMD and press Enter. This will open the command prompt window where we can run network commands. Step 2. Run the ping command now in the command prompt. Type the following: pinggoogle.com, then press Enter. What this does is send small packets of data from your computer to Google's servers. Step 3. Understand what happens. Your computer will attempt to contact google.com behind the scenes. The system first resolves google.com into an IP address. Then it sends packets to that IP and waits for a response. If everything is working correctly, you will see the following replies coming back. Let's analyze this ping result together. But this time, we're going to think like a SOC analyst in a real-world environment. Remember, we are not just running a command, we are interpreting network behavior. Step 1, understand the context. Before looking at the numbers, ask yourself, why is this system communicating with google.com? In most environments, this is normal. Users access Google services regularly, so our baseline expectation is simple: a trusted destination, stable communication, consistent performance. Now, let's validate that using the data. Step 2, destination analysis, also known as trust verification. We see google.com with the IP address 142.250.117.100. As a SOC analyst, you don't just accept this, you validate it mentally. Does this IP belong to Google? Yes. Does it match the domain? Yes. Is this communication expected? Yes. So the conclusion is clear. The destination is legitimate, but always think ahead. If this IP was unknown or didn't match the domain, this could indicate DNS manipulation or malicious redirection. Step 3, reliability analysis or connection health. We check sent equals 4, received equals 4, lost equals 0. This tells us there is no packet loss. Communication is stable. There are no interruptions. As a SOC analyst, you interpret this as this system can reliably reach the destination. There is no indication of network disruption or filtering. But again, think critically. If packets were being dropped, you would ask, is there network congestion? Is a firewall blocking traffic? Is something interfering with communication? Step 4, performance analysis, also known as latency behavior. We observe response times of 28 milliseconds, 29 milliseconds, and 30 milliseconds, with an average of 29 milliseconds. This shows fast response times, very consistent timing, no spikes or anomalies. As a SOC analyst, you would say, this is stable and expected latency for this type of connection. But if things look different, you would investigate. For example, high latency, like 300 milliseconds or more, sudden spikes in response time, or irregular timing patterns. These could indicate routing issues, connections to remote or suspicious servers, or even malicious communication behavior. Step 5, behavior analysis. This is the most important step. Now we bring everything together. Ask yourself, does this behavior match the normal baseline? What do we see? The same IP address throughout, no packet loss, consistent response times. This is predictable and stable behavior. So the SOC conclusion is, this communication is normal, trusted, and healthy. There are no indicators of compromise or suspicious activity. But always think ahead. What would make this suspicious? As a SOC analyst, you would investigate if you saw unknown or changing IP addresses, packet loss or failed responses, high or inconsistent latency, or communication happening at unusual times or frequency. These are all signs of potential threats. Final takeaway. As a SOC analyst, you are not just checking if something works. You are constantly asking, is this expected? Does this match normal behavior? Is there any anomaly? Your job is to detect the smallest deviation from normal. Because in cybersecurity, anomalies are often the first sign of an attack. And remember this, tools like ping are simple, but in the hands of a SOC analyst, they become powerful tools for understanding, analyzing, and defending network behavior. Let's now focus on the core duties of a SOC analyst and how these responsibilities are carried out in a real-world environment. One of the primary responsibilities of a SOC analyst is continuous network monitoring. This means you are constantly observing network traffic, system activity, and logs and alerts, not occasionally, but 24/7. As a SOC analyst, you are always asking yourself, what is happening on the network right now? Does this activity look normal? Is there anything unusual? In a real SOC environment, analysts use tools like SIEM platforms to monitor login attempts, data transfers, and connections between systems. The goal is simple: detect anything that deviates from normal behavior as early as possible. Next is detecting anomalies. An anomaly is anything that does not match expected behavior. For example, a user logging in at an unusual time, a system connecting to an unknown IP address, or a sudden spike in network traffic. At this point, the SOC analyst mindset kicks in. This doesn't look normal. Could this be a threat? SOC analysts are trained to recognize patterns, identify deviations, and prioritize potential risks. Because anomalies are often the first sign of a security breach, and remember this, not every anomaly is an attack, but every attack starts as an anomaly. Once something suspicious is detected, the next step is investigation. This is where SOC analysts dig deeper. They analyze alerts generated by security tools, system and network logs, and user activity. At this stage, the key question becomes, what exactly is happening here? Is this a false alarm or a real threat? During investigation, analysts aim to understand the source of the activity, determine the severity of the threat, and identify any affected systems. Based on their findings, they may escalate the issue, contain the threat, or confirm that the activity is safe. All of these responsibilities form a continuous cycle: monitor, detect, investigate, respond, and repeat. Here's the key takeaway. As a SOC analyst, your role is not passive. You are actively watching the network, detecting unusual behavior, and investigating potential threats. Your goal is to identify and stop threats before they cause damage. And it all starts with one critical skill: understanding what normal looks like so you can quickly spot what isn't. Let's now talk about networks and why they are so important in cybersecurity. At the core of all digital systems are networks. Networks connect devices, systems, and users, allowing them to communicate and share data. Without networks, there would be no internet, no cloud services, and no communication between systems. This is why networks are considered the backbone of cybersecurity. They provide the infrastructure through which all digital communication happens. But here's the key point: the same networks that enable communication also create opportunities for cyber attacks. Every network has potential weaknesses, also known as vulnerabilities. These vulnerabilities can exist in misconfigured systems, outdated software, or weak security controls. Attackers actively search for these weaknesses, and they exploit them through network communication. For example, malicious traffic sent to a system, unauthorized access attempts, or hidden communication between compromised systems. In many cases, attackers do not need physical access. They use the network as their entry point. This is where cybersecurity becomes critical. To protect networks, we must understand how the network is structured, monitor traffic continuously, and identify anything unusual. SOC analysts play a key role here. They analyze network traffic, logs, alerts, and communication patterns. Their goal is to detect threats early and prevent attacks before they cause damage. As a SOC analyst, you are always asking, what does normal network traffic look like? Is this communication expected? Is there any unusual behavior? Because attacks often hide within normal-looking traffic. Here's the final takeaway. Networks are the foundation of cybersecurity. They enable communication, but they also introduce risk. Understanding networks, identifying vulnerabilities, and monitoring activity are essential skills for detecting and preventing cyber attacks. And this is why networking knowledge is critical for anyone starting a career in cybersecurity. Let's now recap the key network fundamentals we've covered and connect them to cybersecurity and SOC operations. At the core of network communication are IP addresses and ports. Every device on a network has an IP address. This allows it to be uniquely identified and reached. Ports act as entry points on a system. They ensure that incoming data is directed to the correct application or service. Together, IP addresses and ports allow devices to locate each other and communicate effectively. Without them, structured communication would not be possible. Now, while IP addresses are essential, they are not easy to remember. This is where DNS comes in. DNS translates human-friendly domain names like google.com into IP addresses. This allows users to access websites and services easily without needing to remember complex numbers. DNS acts as the bridge between humans and machines. When we bring these elements together, we get a complete communication flow. A user enters a domain name. DNS translates it into an IP address. The device sends a request to that IP using a specific port. The server processes the request and sends a response back. This structured flow ensures communication is reliable and efficient. Now let's connect this to cybersecurity. SOC analysts rely heavily on these fundamentals. They monitor network activity and analyze IP addresses, ports, DNS requests, and communication patterns. Using this information, they detect unusual behavior, identify threats, and protect systems. As a SOC analyst, you are always asking, is this IP address expected? Is this port being used correctly? Is this DNS request legitimate? Does this communication flow look normal? Any deviation from normal could indicate a potential threat. Here's the key takeaway. IP addresses, ports, DNS, and communication flow form the foundation of networking. And these same fundamentals are what SOC analysts use every day to monitor, detect, and respond to cyber threats. If you understand these concepts well, you are building a strong foundation for a career in cybersecurity.